In this video, we are going to review what you have learned in the first 3 lessons of this chapter. This chapter is all about what we call exponential functions. It's a new type of function, and the pattern that we see in exponential functions is that we either multiply or divide by the same number each time to get the new value. So the way you began in this unit was talking about what's called a geometric sequence. Now, a sequence is just a series of numbers that have a pattern. So for example, if I were to start with the number 2 and multiply that times 3, 2 times 3 is 6, and continue multiplying by 3, that's an example of a geometric sequence, multiplying by 3 each time. Now you can also multiply by fractions. So for example, let's say I was going to start with 20 and multiply times 1/2. Half of 20 is 10. Half of 10 is 5. Half of 5 is 5 over 2. And I could continue with that pattern. So a geometric sequence is a list of numbers where you are multiplying by something each time to get the next number in the sequence. So let's look at example 1. Determine if the following sequence is geometric. If so, write the recursive and explicit rules for it. If not, explain. So before I do this example 1, let me review with you what the recursive and explicit rules are for geometric sequences. Now recursive, that's when you just in sequence find the list of numbers. So if you know a certain term or a certain number in the sequence, the recursive rule will tell you how do you get the next number in the sequence. So this is how it starts. You have to say what the first term of the sequence is. So for example, the example that we have over here, A1 would be 2. And then to get a term in the sequence, you take the term right before it, that's what a sub n minus 1 means, and you multiply it times the common ratio. So in this example again of 2, 6, 18, and 54, 3 is that common ratio. That's what you're multiplying by each time. So that is the recursive rule. You're going to want to make sure and have this on your notes. Hint, hint, wink, wink, nudge, nudge. Okay? And then for the explicit rule, this is for when you can find any term in the sequence. It's just kind of a plug and chug situation. To find any term in the sequence, you start with the first term and multiply the common ratio to the n minus 1 power. So for example, if I were to use the explicit rule and try and see if I can get these numbers here in purple, if I wanted the third term in the sequence, the initial value of that sequence was 2, the common ratio is 3, and if I want to find the third number in the sequence, you put 3 in for n. 3 minus 1 is 2, so this is 2 times 3 squared. Remember order of operations, we do exponents first. 3 squared is 9, 2 times 9 is 18. So is the third term of the sequence 18? It sure is. So that's what the explicit rule means. So what we're going to be looking at in example 1 is those lists of numbers and seeing, is it a geometric sequence? And if it is, we're going to write these 2 rules for it. So let's take a look at this one. 1 times 4 gets me 4. 4 times 4 gets me 16. 16 times 4 gets me 64. So this is a geometric sequence because I'm multiplying by 4 each time. So let's do the recursive rule. The first term in the sequence is 1. And to get the next term in the sequence, I take the one right before it and multiply times 4. So again, in order to write the rule, I needed the first term of the sequence and what we're multiplying by. When we do the explicit rule, I need those same two pieces of information. So to get a term in the sequence, I need the first term times my common ratio to the n minus 1. Okay? All right. Next one. We start with 128, go to 64, go to 32, go to 16. So I'm getting smaller. So think about this example that I put up above, going from 20 to 10 to 5 to 5 halves. The pattern there was I was multiplying times 1/2. Well, let's see if that's the pattern here. What is 1/2 of 128? Well, if you're not quite sure, you can find what's half of 120 and what's half of 8 and put that together. Half of 120 is 60, half of 8 is 4. Together that makes 64. And bingo, that's what we have there. Let's see what half of 64 is. Well, if you're not sure how to do that, break 60 and 4 apart. Half of 60 is 30, half of 4 is 2. Together that makes 32. And half of 32 is also 16. So this pattern is working to get each number. So this is also a geometric sequence. So let's do the recursive rule. The first term of the sequence is 128. And the rule is a sub n equals a sub n minus 1 times our common ratio, which was 1/2. The explicit rule is the first term of the sequence, which was 128, times the common ratio, which is 1/2, to the n minus 1. Okay. So that's how we write recursive and explicit rules given the list of numbers. Let's look at this next one. The first term of a geometric sequence is -3, and the common ratio is 2. Find the 8th term. Now, you have a couple of choices. You can start with -3 and multiply times 2 until you get to the 8th term. Or you can write an explicit rule and plug in 8 for n. That's the route I'm going to go. So remember, an explicit rule looks like this. So I need to know the first term of the sequence and the common ratio. The first term of the sequence, they told me, is -3, and the common ratio is 2. So if I want to find the 8th term of the sequence, we're going to replace n with 8. Now remember, exponents do that first. 2 to the 7th. Then I need to simplify 2 to the 7th, and I believe that's 128, but let me double check on my calculator. that is 128. And then I'm going to multiply negative 3 times 128, and we get negative 384. So that means the 8th term is negative 384. Okay, but again, you could have just started with negative 3 and multiplied times 2 and you did that 7 times until you got the 8th term of the sequence. Okay, so that's some examples on 9.1. You can either pause the video and do the practice problems now, or you can keep watching so you can get the notes for what you need for the other lessons and then do all the practice problems at the end. That's up to you. Let's move on to the next. So we're going to tell whether each set of ordered pairs satisfies an exponential function and explain our answer. This is very similar to what we just did, because what we need to do is we need to look at the y values here and see if I multiply by something, do I get the next value in the sequence? Well, 10 times 2 is 20. If I do 20 times 2, we get 40. If I do 40 times 2, we get 80. So this is an exponential function. So geometric sequence and exponential function, they are in some ways one and the same thing. So we would say yes, and my reason here would be because, and I'm going to shorten because like that, there is a common ratio. Let's look at the next one. I need to look at my y values, or the second number in my ordered pairs here. Let's see, 5 times what gives you 10? That's 5 times 2. Is 10 times 2 equal to 15? No, it's not. So this is a case of where we're not multiplying by the same thing to get the next value. This is not an exponential function because there is no common ratio. Okay? All right, let's review how to graph an exponential function. So if I've got a graph here, and I'm going to write this a little bit bigger. I know you've got it on your notes, but I'm going to write a little bit bigger, 3 to the x. I'm going to graph this by making a table of values. And I'm going to use negative 1, 0, 1, and 2. So I'm going to plug each of these in. 3 to the negative 1 is 1/3. So that means I'm going to plot the point negative 1, 1/3. Plug in 0 for the exponent. Anything to the 0 power is always 1. So that means I need to plot that point. 3 to the first power is 3. So I'm going to plot 1, 3. And then 3 squared is 9. So that means I need to plot the point 2, 9. So I'm going to plot these 4 points. Negative 1, 1/3 is just a little bit above the x-axis. 0, 1, 1, 3, and 2, 9. Now be careful when you connect these dots. Remember, there is what we call an asymptote. And in this case, the asymptote is the x-axis. That means it does not touch or cross the x-axis. Now let's talk about some transformations. So in example 3, it says let f of x equal 2 to the x. Whoa. Then it says write the function rules for g of x and h of x based on the descriptions given. So in part A, it says g of x is a translation of the graph of f of x, right 4 units and up 3 units. Remember, when I move to the right or to the left those lie. So right 4 is actually x minus 4. And that's what the exponent is going to become. Now, I don't have to put parentheses around x minus 4 because it's being held up together in that exponent. If you put parentheses around it, I won't count that wrong. And then we need to do the up 3 units, and that's just simply plus 3 at the end. So there is my new function. For the next one, we're still using 2 to the x. And it says h of x is a vertical stretch of the graph of f of x by a factor of 5 and a vertical translation 1 unit down. Vertical stretch is multiplying times something. And the factor of 5, that tells me what I'm going to multiply by. 5 times your function. And then translation 1 unit down is minus 1. So the way this is going to look is 5 times 2 to the x. And then make sure the minus 1 is not put in as an exponent. Okay? So again, you can either pause this video and do the practice problems for 9.2, or you can keep going and get the notes for the whole review and then do the whole review at the end. So, last section here, 9.3. 9.3, this is where we talked about real-world examples of exponential functions. And we had 3 basic formulas. This was exponential growth. And you're going to want to have these on your paper as well. This is exponential decay. Again. And then we had what we call compound growth. Now, compound growth is when whatever you're increasing by is calculated more than once a year. So the words we might see associated with these types of problems are words like monthly, or quarterly. Monthly would be 12 times a year, quarterly would be 4 times a year. So we're going to be writing exponential functions using these 3 formulas. Again, you're going to want to make sure and have these on your notes because these are very important formulas and you're going to want to have easy access to them. So let's take a look at example 1. Write an exponential growth function. So they've given us a clue here that's going to be a growth model to model the situation. Then find the value of the function after the given amount of time. So we're going to have 2 pieces to our answer. We're going to have a formula answer and then a number. So let's look. Annual sales for a clothing store are $270,000 and are increasing at a rate of 7% per year for 3 years. So this is what I'm going to use to get my number answer, the 3 years. But I'm going to need to use this 270,000 and the 7% to get my formula. Now remember, when you put a percent into the formula, it's not 7, it's 0.07. You've got to move the decimal place over 2 times to the left. So since this is exponential growth, we're going to be using this first formula. P stands for principal, or the initial amount, which is the 270,000. 1 plus my rate, which again is 0.07 to the t. That is my model. That's my formula. But then what we're going to do to get our number answer is I'm going to replace t with 3 and put that into the calculator. Where did I get the 3? It's from the 3 years that they gave me in the problem. So 250,000 times 1, or parentheses 1 plus 0.07 parentheses to the third. And if you put this in correctly, you should get $306,260.75. Okay. All right, let's look at the next one. Right, a compound interest function. So they gave us a clue here, compound interest function. We're going to be using this formula, the third one, to model the situation. Then find the balance after the given number of years. So same situation, we're going to have a formula answer, then a number answer. So let's see what the scenario says. $35,000 invested at a rate of 6% compounded monthly for 10 years. So monthly, that means 12 times a year. So our formula is going to be our initial amount, which is 35,000. We're increasing at a rate of 6%, which again, as a decimal is 0.06. Actually, hold on. So that means, again, if I'm using this third formula here, I'm going to put 0.06 up in R in that spot. Then I'm going to divide by 12 because it's the number of times it's compounded each year, times 12t. Now, we can leave that as our formula answer or our model. But then when I plug this in, we're going to put in 10 for t, and I would suggest, before putting this into the calculator, that we figure out what this fraction, 0.06 divided by 12 is. And that is 0.005. So what I would put into the calculator is this. 35,000, 1 plus 0.005, and then what's 12 times 10? 12 times 10 is 120. I would go ahead and write that as 120. So I'm putting this in 35,000 parentheses 1 plus 0.005 to the 120th power. And if you put this in correctly, you should get 63,678.89. And in this context, it still makes sense to put 0.89 because we're talking about money. Pay attention though, we might see a situation where it does not make sense to have a decimal. That would be like if we're looking at people or objects, it doesn't make sense to have part of an object. So let's look at the next one. Write an exponential decay function to model the situation, then find the value of the function after the given amount of time. So the population of a school is 800 and is decreasing at a rate at 12% per year for 4 years. So the model that we're going to be using in this case is the second one, 1 minus r. Now our rate is 0.02, so it looks like this. P, our initial amount, is 800. 1 minus our rate to the t. That is our model part of the answer. And then to finish it out, to do our number answer, we're going to plug in 4 for t. So I'm going to put this into my calculator. It's just I'm going to put 4 in for t. And if you plug that in correctly, you should get 737.89. Now, we're not talking about money in this situation. We're talking about people. So does it make sense to have 0.89 of a person? No. So what we need to do is we need to round this to the nearest whole number, which in this case would be 738. So 738 people would be the answer. Or students, I guess we could also say. All right. So depending on where you're at, when you're watching this video and when you're working on this review assignment, you're going to be taking a quiz over this material. So it might end up being the same class period that you're working on these problems, or it might be the next class period. So that's why I say it's very important that you have both these formulas and the recursive and explicit formulas. Make sure you have those on your paper, because I'm going to let you use this review packet when you take your quiz. Okay?